In this video, we will talk about the triangle inequality theorem. So here's what this theorem says. It says the sum of the lengths of any two sides of a triangle must be greater than the length of the third side. So just to get an idea of what that means, if we have some triangle, remember a triangle has three sides. Let's say the length of this side right here is 10. What this theorem says is that the length of these other two sides, so this side and this side, must be greater than 10 for this to actually form a triangle. So for example, this side could be maybe like a 6, and this side could be like 5. So 6 plus 5, that's greater than 10. So those are perfectly valid values. Or maybe this side could be an 8, and this side could be like a 4. So an 8 plus a 4 is greater than 10. So those are perfectly valid values. But what wouldn't be valid is, let's say if this side was 10, and this side was, say, 5, and then this side was like 3. So 5 plus 3 don't add up to 10. So these two line segments would not be able to join right here to actually form a triangle. And even if we laid these line segments almost completely flat, so if this was like a 5 right here and this was a 3, they still wouldn't quite reach to form a triangle because 5 plus 3 can't span this distance of 10. So that's what this theorem is saying. The sum of any two sides of a triangle must be greater than the third side. So with that in mind, let's check out a couple examples of how we can use this theorem. Alright, this problem asks us, determine if the following values can be measures of the sides of a triangle, 3, 2, and 6. So can these three values, can they be the measures of the sides of a triangle? So here's the process we can use to determine if they can be. First, write them in order from smallest to largest. So we'll say 2, 3, 6. So we write them from smallest to largest. Next, we just have to ask ourselves, when we add these two smaller values together, this 2 and this 3, are they greater than 6? So 2 plus 3, that's 5. Is 5 greater than this third value of 6? So is 5 greater than 6? No, it's not. So we would say, no, these three values could not be the measures of the sides of a triangle. And if we were to visualize it, if this side of the triangle is 6, and let's say this side is 3, and this side is 2, these two sides are not long enough to span this distance of 6 to actually form a triangle. So that's why we say no, the values 3, 2, and 6 cannot form a triangle. All right, let's try another one. Determine if the following values can be measures of the sides of a triangle, 7, 5, and 10. Can these three values form a triangle? So once again, we'll write them in order from smallest to largest. So we'll say 5, 7, 10. And we'll use the same process. Let's add the two smaller sides, so 5 plus 7, that's 12, and ask ourselves, is this greater than the third side? So is 12 greater than 10? Yes. So we would say yes. These three values can form the sides of a triangle. And if we were to visualize it, if we had the triangle and this side was 10, and this side was 7, and this side was 5, these two sides are greater than the value of 10, so they're long enough to span this distance of 10 and actually form a triangle. Now you might be thinking to yourself, well, the theorem says that the sum of the lengths of any two sides of the triangle must be greater than the length of the third side. So shouldn't we have to check the other combinations as well? Shouldn't we also have to check, well, is 5 and 10 greater than the third length of 7? Well, 5 plus 10, that's 15, so it's greater than 7. And shouldn't we also have to check if 7 plus 10 is greater than this missing length of 5? Well, 10 plus 7, that's 17 is greater than 5, so that checks out. But by doing this method, by only checking if the two smaller sides are greater than the third side, this is the only step we have to do, because if these two sides are greater than the third length, it must be true that the greatest length, so the third side, plus any of these two smaller sides, must be greater than the missing third side. So this is just kind of a shortcut you can use by placing these three values in order and just checking if the two smaller sides are greater than the third side. This is the only step that you have to do, rather than checking all possible combinations. All right, let's try another example. Determine if the following values can be the measures of the sides of a triangle, 12, 4, and 6. Can these three values form a triangle? So again, we'll write them in order from smallest to largest. So we'll write 4, 6, 12. Then we'll ask ourselves, can these two smaller sides, are they greater than the largest side of 12? So 4 plus 6 is 10. Is this greater than 12? No, it's not. So these three values could not form a triangle. All right, let's try one last example. Determine if the following values can be measures of the sides of a triangle: 5, 5, and 10. Could these values form a triangle? Well, let's write them in order from smallest to largest. So it looks like it's already in order. So 5, 5, and 10. And we'll ask ourselves, if we add the two smaller sides, so 5 plus 5, that's 10, is it greater than this third side? Or in other words, is 10 greater than 10? No. 10 is equal to 10, but it's not greater than 10. And if we were to visualize this one, if this triangle had a side of 10 and these ones both had sides of 5, it would be very close to forming 10, but it couldn't quite form 10. And even if the angles were almost completely horizontal, they still wouldn't quite touch each other, and they couldn't span this distance of 10. So keep that in mind. The theorem says that any two sides have to be greater than the third side, not just equal to it. So we'd say no, 5, 5, and 10 could not be the measures of the sides of a triangle.